Okay, good morning, everyone. Quantum mechanics, as we all know, uh, like there are so many things that can be covered under quantum mechanics. So rather than fixing what I want to teach, I decided that I will interact with all of you because I am told that you are from BTech, MSc, and BSc, right? So uh, generally, my plan for today's class is about equation of motion and matrix mechanics, right? I want to focus on that aspect. Uh, how many of is there anyone who has not learned quantum mechanics or fundamentals of quantum mechanics, or can I assume basic concepts of quantum mechanics that you all have covered in your BTech or BSc MSc courses? Yes, right. Okay. What about those online? I can see only two people in the classroom.
Yeah, so people offline, they have taken the course on quantum mechanics.
Right, sir. So Bala sir will take the advanced part. I would like to focus on basics, and depending upon today's lecture, we will decide the course of our learning in the upcoming 4 lectures. Right. So please do participate in the interaction and discussions. I will be putting some questions. I will be writing some equations where I will ask you that how did we get that? So I can get an idea if we need to cover some uh, mathematical aspect or tools or some sub concepts which are part of the discussion. Okay, so I will be sharing the screen now and I will be doing work on my tab and you will be able to see the work. Maybe my camera will be switched off because when I'm sharing that, my camera is suddenly getting turned off, right? But I'm able to hear you, everyone. So can someone in the classroom speak something so I can confirm whether I can hear you? As I said, we want to discuss the equation of motion and matrix mechanics. Right? Why equation of motion? Why are we beginning with that? Because just you have, I think, undergone the lecture of Sheetal Rawat ma'am, right? Classical mechanics. What do we do that? We study the dynamics of given system in given state, right? And we try to describe the evolution of the system with time. Okay. How do we describe it? In terms of dynamic variables. Fine. So it is described by dynamical variables. Which are they? What are the dynamical variables in classical mechanics? Position coordinates, right? And the velocity. Or you can say momentum and position, right? So your position and the velocity, right? It describes the evolution of the system. And the differential equation that you observe for a given system is called the equation of motion for a given system. Okay. Similarly, in quantum mechanics, instead of position and velocity, the system is described by what? It is described by some vector in Hilbert, abstract Hilbert space. Okay. And these vectors, what do we call them? We call them state vectors. Right? So it is, so in quantum mechanics, equation of motion is a differential equation of state vectors. Very simple, right? But the quantities of state vectors, how do we, but is it now wise to compare the classical system with quantum? No, because there is a concept that we all know, expectation value, right? You need to observe the expectation value because what we are doing is that here in the classical mechanics, we see the evolution of position coordinates and velocities. Here we are focused on state vectors, right? So in quantum, observable quantities are not state vectors, but the expectation values of the operators which are corresponding to the dynamic variable. So there is an operator correspondence. Hello. Okay. So what, again, I am repeating the statement here. What we are doing in quantum, what we are doing actually in quantum mechanics is that we are trying to solve the equations, right? Differential equation, not of the state vector, but the observation expectation value, right, of the dynamic variables, which are the Hermitian operators corresponding to given variable, whether it's a momentum, whether it's a position, or any other, right? Okay. Let me write and then we can go ahead. So how do we find the expectation value of any operator, right? You all know that we find, let's say, if we have an operator A, then its expectation value is found by the bracket notation of psi A psi, that is bra psi A cat psi. Are you all aware about the bracket notations?
Yes, sir.
Fine. Are you all aware about the Hermitian operators?
Yes, sir.
Perfect. Okay. Now, the variation of this expectation value, right? It can happen in two ways with reference to these state vectors, right? So psi is our state vector. What are the possibilities of the variation of expectation value with time? There are three possibilities, right? That this quantity, it can vary in three ways. Number one, that state vector psi, it varies with time, right? And our operator expectation value of A, it is independent of time. Second scenario, let's reverse the role, right? That our operator A, it varies with time and psi remains constant. And there is a third scenario. Both state vector and our operator A and psi vary with time. So these three scenarios are given three different titles. Scenario one is called the Schrodinger picture. Scenario two is called the Heisenberg picture. And scenario three is called the interaction picture. Right? So we know these terms and we will go through all these three scenarios today. That's my target. Okay. So first scenario, when your state vectors change with time, but your operator, which is corresponding to dynamical variable, that is, let's say A, is independent of time, then that scenario is your Schrodinger picture. Fine. Then if your operator, which is corresponding to dynamical variable, is changing with time while your state vector remains constant, it's the Heisenberg picture. And when they are both changing with time, then there is some interaction happening and it's called interaction picture. Okay. So of course, this is true. And okay, in terms of real point of view or real physical observation aspect, let's say we are somehow able to observe some quantum phenomena, right? Then this variation of expectation value of our dynamic variable A, right? Whether it remains constant or it is changing in cases, right? It must be the same as what we do find the value in terms of observed readings or data that we take experimentally. Fine. So yes, this must be kept in mind. Okay. So whenever you are calculating expectation value of any quantity, it must agree with the observed value or the observed rate of change of that dynamical variable quantity. Okay, so let's now begin with the Schrodinger picture. Fine. So simple, our state vector that is wave function psi, right? It must vary with time. So psi, it is function of time, right? And our operator A is not function of time, right? Now, in every quantum mechanical system, there must exist a linear operator. Let's say a one linear operator U, which is function of t and t0, right? Which is defined in our Hilbert space. Now, our Hilbert space is infinite dimensional Hilbert space, right? I hope you are all aware about the linearity of the function, right? We will also look at the unitary operator and we will discuss if required in detail. Fine. You may stop me, raise question anytime. Fine. So let's say there exists some linear operator U, which is function of time. Obviously, T0 is the time where at the beginning and T is the time when we are defining the time duration, right? During which our state vector is changing and our operator A, which is corresponding to dynamical variable, is fixed. Fine. So going ahead, here this function U, which is function of T and T0, what we can call is that it is kind of a time evolution operator. Or in another word, we can also call it a time development operator. Okay. Now, since we know that state vectors or wave functions can be normalized, I can write that psi t0 in bracket notation is equal to 1. Similarly, at time t, our state vector psi t is equal to 1, right? Because our psi is normalized. That's what we are considering. So what will follow from here is that if we say that this UTT0, sorry, right? It's a time evaluation operator. It's a linear operator of our infinite dimensional Hilbert space. Then I can follow that the same equation can be rewritten for, let's say, for psi t, this will be U t0, which operates over the wave state vector at t at the beginning, right? And UTT0 psi t0. Fine. Now, since it's a normalized, that means I can, okay, I hope adjoint, you are aware about the adjoint as well?
Yes, sir.
Yes, yes. So I will write it. If you have any query, concern, you can just ask me anytime. Okay. So this will then transform into what? I can rewrite this as psi t0 u dagger tt0 u tt0, which is our linear operator psi t0. Fine, which is also supposed to be 1, right? So what does this mean is that if
Could you explain this part just?
yes, I'm going to the unitary operator part only, right? So if this is possible, if the evolution operator, that is our U operator, U tt0 is an unitary operator, right? What does this mean? It means that that this operator has to be a Hermitian operator, right? and its adjoint u dagger u or u dagger t0, I will write it properly, right, is supposed to be equal to u t0, u dagger t0 is equal to 1, which will follow that u dagger represents u inverse of tt0. Now you also, if you are not aware about the inverse operator, right, here, when can we have a, we don't get inverse, or we don't have inverse operator always. Just like in matrix, you can have an inverse of a matrix under certain condition. Similarly, here the inverse operator is going to be there if that operator itself is unitary operator. Okay. Sir, what was your question? I think Gurudat sir, you asked about this derivation, right?
No,
Hello.
it was somebody else. Yeah.
Okay, okay.
Sir,
Yes, yes.
sir, the above part where the operator, yeah, this one,
Uh,
the
this
above,
particular part.
yeah, yes.
Perfect. Okay. What is the question?
I mean, how it transform into this one.
Okay. So, fine. Excellent. So we will just quickly see the Hermitian and co-Hermitian operation, right? And some of the, we can discuss the adjointness of its property, right? When is an operator a Hermitian operator? I am write in the red ink so it doesn't mix up with our routine write-up. So if operator A, right, is equal to its adjoint, it's an Hermitian operator. Fine.
Yes, sir.
That means if our state vector psi, right, and let's say we use another vector phi for a understanding purpose, then this is going to be equal to phi a cap psi. Fine. So what it will lead us to? What is the adjoint? Hello. Please, or those who are in the class, please interact, right? I like this way.
May I answer?
Yes, yes, yes. Hello. Please go ahead.
Hello.
Yes, sir.
Yeah, if we have,
Is Gurudat sir, is it you?
I am using Gurudat sir's microphone since there is a certain echo in
Okay,
the
okay, okay,
classroom.
okay, okay. Yes, yes, yes.
If we have an inner product
Mhm.
between psi and phi,
Correct.
instead of that, if we have an inner product between A acting on psi and phi, then
Fine.
the adjoint is defined by it should be the same as some other
Exactly.
operator, A dagger acting on the inner acting on phi,
Exactly.
paired with psi.
So I will write what he said in what he said in words in terms of an equation. So what he is saying is that the bracket notation, I'm using the bracket notation, right? It should be equal to phi psi. Am I right?
Yes.
Right. So if operator A, right? As he said, the scalar product, right? If some, let's say, scalar is alpha A cap psi is there, then it will be alpha A cap psi, and vice versa, right? But in this case, since it's a Hermitian, A cap will be A cap dagger, and they are both the equal. And that's what it follows over here in this particular discussion. So now what we will do is that we will obtain some explicit expression for unitary operator, right? Considering time dependent Schrodinger equation. So let's first, we will use it. We will go ahead with our regular discussion, and then we will come back to the this expression of unitary. Ma'am, I'm delivering a lecture. Can I call you in few minutes? Yes, yes, fine. Okay. Am I audible again? Hello.
Yes, sir.
Hello. Okay. Screen is also visible.
Yes, sir.
Perfect. So what I was saying, yes. So what we'll do is that we'll obtain the expression for unitary operator. But before that, let's write our Schrodinger equation in time dependent format, right? So it will be IH cut del psi, because that's what is our state vector, is equal to H psi t. Okay. So now let's integrate this equation. So what will happen is that it will become integral T0 to T del psi by psi is equal to 1 upon IH cut, the Hamiltonian integral T0 to T del T. It will turn out to be ln psi t T0 to T is equal to 1 upon IH cut Hamiltonian T minus T0. So if I make my psi, which is varying with time, as my subject, it will be e to the power 1 upon IH cut. This is I, H cut, into Hamiltonian into T minus T0 psi of T0. Fine.
Yes,
Now
sir.
what we will do is that we'll use our initial equation. Let's give it some number. Where did we write it? That's psi. Okay, so yes, the point is our psi, it is evolve. I will write it again, right? So our psi, how did we begin? We began by considering operator UTT0, which is our development operator, right? That is, we say that psi t is u t t0 psi t0. Fine. Now we have this equation with us. We have this equation with us. Okay. So if we use them, we will obtain the expression for the time development for operator UTT0, right? So you use these two equations. Come on, everyone. Please do it in your notes. And we will get UTT0 as the output. Okay. And I just changed the pen for the making sure that it's our subject. What it will be? Simply e to the power 1 upon, let me zoom out a little bit so you can see both equation, 1 upon IH cut. It is very simple comparison. Correct? Simply, it's directly visible. There is nothing to get confused. Okay, so we can use it. I can rewrite it again, 1 upon IH cut, I square, I multiply, I square is -1. I can write it e to the power minus I upon H cut Hamiltonian into T minus T0. Now remember, here our Hamiltonian itself is Hermitian. Okay. Our operator U T0, it's unitary. Right? Then if considering this, if I rewrite this time dependent Schrodinger equation, okay, just look at the entire picture. Then it will be IH cut del U TT0 by del T is equal to Hamiltonian into U TT0. Right? So that means unitary operator obeys the differential equation. Now in that case, what we will do is that we will look at the rate of change of expectation value of operator A. Because if it is changing or not, that's what we want to find out. According to Schrodinger picture, only psi has to change, A does not. So what better result than finding the expectation value? So the next task is to find the rate of change of expectation value of operator A, right? So d by dt of our dynamical operator A, how do we write it from the definition of expectation value? Simply psi t A psi t bracket notations. What will happen? I will quickly write the derivation. It is very simple. D psi by dt A psi plus psi A d psi by dt. Now, what is this? This is simply d psi by dt. We can write from our previous equation here, right? D psi by dt, we can make it subject. Okay, so it will turn out to be 1 upon or I upon h cut. So I will get I upon h cut out. Then it will be h psi A psi plus, and then one since I have kept I square upon I, it is going to be minus psi A h psi. You can work out in two steps. You can see you will get the same derivation. I will give you 2 minutes to look at that steps. Right? So this is psi HA minus AH psi. And this is nothing but commutator relationship between our dynamical variable A and the Hamiltonian H. So, okay, so let me write this expression properly. D by dt A is this. So what does this follow is that here, if my d by dt of expectation value of A, when it is 0, what will it indicate? It indicate that A commutes with Hamiltonian H. And consequently, what will happen? It means that A is constant of motion. Simple.
Yes.
Now, so this is your Schrodinger picture. When we can say that A depends explicitly on time? So in physical systems, so this is how we deal with the Schrodinger picture. Now to move to Heisenberg picture, where your A varies, that is your dynamical variable operator, corresponding operator of dynamical variable is varying with time. Now this may happen, what we say is, let's say in terms of external force or external field is there, which is present, then in that case, what will happen is that it will change slightly by, this equation will vary to, let's say, some equation like this, del A by del T plus 1 upon IH cut A commutation relation with H. I hope you all have, you all can relate the commutation relation to larger understanding of how it is interacting. The dynamical variable is associated with the Hamiltonian itself being Hermitian operator, right? The orthogonality and everything, all aspect which is associated with the algebraic part. Okay. So yes, this is your Schrodinger picture. Now let's move to the Heisenberg picture. Okay, so here in Heisenberg picture, we will definitely look at this portion only, but we will begin from the beginning. Okay. So in the Heisenberg picture, let's move there. Okay, any question, any discussion you want to do before we follow? Or can we go ahead with the Heisenberg?
Just a doubt.
Yes.
While solving the differential equation, you pulled the Hamiltonian out of the integral.
Wait. Let me go there. Over here.
Yes.
Yes.
So can the same process be done when the Hamiltonian is explicitly a function of time?
No, definitely not. So what we are going to see is that in our okay. So next in Heisenberg picture. So let me give you an highlight that what happens in Heisenberg picture, right? In Heisenberg picture, we will give the state vector some fixture, right? That it is only your dynamical observable quantity which is varying, right? So when you are talking about Hamiltonian associated with the dynamical variable, we will see relationship between A and H. Actually, see, the time derivation of Hamiltonian comes later in interaction picture where it is explicitly dependent upon time.
Right.
Right.
We are in Schrodinger picture right now. Okay. Okay.
Right.
Okay.
Right. So that's why, yes, you got it, right?
Yes, sir.
So the Heisenberg picture, let's discuss that. Okay. Okay, so what is our Heisenberg picture? We all know state vector is time independent, right? And our dynamical operator is time dependent. Fine. So here, to avoid confusion between the previous one, what we will do is that we will write A as AH and psi as psi H. So Heisenberg picture is differentiated from the Schrodinger picture. Fine. Okay. So let's say the state vector, right? Psi in two pictures. One is Schrodinger picture, one is Heisenberg picture. Let's say at the beginning of the time when we are starting to observe the evolution of the system, that is at t is equal to t0, they are the same. That means my psi t0 from the Schrodinger equation is same as psi h t0. Okay, so beginning is the same. That's what we are considering, just like the Schrodinger picture. But in Schrodinger picture, it is psi that varies, and in Heisenberg picture, it is A, that is dynamical quantity corresponding operator, which is going to vary. Fine. So at t is equal to t0, we are saying they are the same. Okay. Now in Heisenberg picture, the state vector psi is not dependent upon time. Our wave function psi is not dependent upon time. So what we will do, we will represent it as the psi h at any time t is equal to psi h at t0. But from our this consideration, it will follow that it is nothing but psi t0. Since it is the same, then we can use the previous case where we represent psi t0 as what? In terms of u, correct or not? Hello. True. So I can write this as u inverse t0 psi t. Now, wait, hold your horses. I will show you why we can write it. Yes, here it is. Right? Okay, please go through these notes as well. Okay, so from psi t, u t t0, psi t0, we are transforming it into this form. Is it clear?
Yes, sir.
Perfect. Because psi t was psi t0, u t t0. So psi t0 will be u inverse t t0 psi t. Fine. Okay. So what we are doing is that it shows that you can go from Schrodinger picture to Heisenberg picture, right? At any given time by unitary transformation. So what we have done, we have used the unitary function ut0, its transformation, to move from Schrodinger picture to Heisenberg picture. Fine. Okay. So now let's write some relations again, and then we will go ahead with the final structure. So UHT is U inverse TT0 psi t. Okay. Similarly, my observable dynamic operator is going to be U inverse TT0 A U TT0, which is same as, you can also write it as U dagger TT0. It's about the representation, right? Otherwise, they are both and the same. Okay. So now let's see Heisenberg picture, that is when A varies with time. So if we differentiate, then it will be dAh, which is function of t, with dt. It will be du dagger dt au plus u dagger a du by dt. Fine. Now we already have equation which will help us in finding this derivation from the Schrodinger case. Wait. Yes, we can use this, right? You can use this. Okay. So if we use this, then du by dt, what it will be? Minus I upon h cut hu, and du dagger by, what will be the answer in that case? Simply I upon h cut. Instead of u, it will be u dagger h. Fine. So now if you substitute these values in the above equation, it will be dh by dt function of time, which will be I upon h cut u dagger h au minus u dagger a hu. Okay. So okay, fine. Let's have a look again, and then we will go ahead with the next procedure. I hope we are going well, right? Okay. Any questions, any discussions that you want to follow?
No, sir.
Okay, fine. So let's focus on what is in our hand. Fine. Now, U is our unitary operator, right? So I can write that IH cut U dagger as it is H. Now I can write here, that is, there is one which is existing there, which I am expressing here as U dagger, correct? AU minus U dagger A, similarly U dagger HU. Perfect.
Yes.
Fine. So that is our unitary operator property, that U cap dagger is identity I. Okay. Similarly, U cap dagger U. So it's up to your requirement or how the operators are arranged. You can use either U dagger or U dagger U. Fine. Okay. Going further, it is IH cut. So what is it? Finally, what we are left with? Can you see? What is HH?
Sir,
it
is the commutator of
excellent.
H, the Heisenberg's H with Heisenberg's A.
Correct.
The dagger on the left side and U on the right side.
Excellent. sorry. Right. So it again land us with the expression that it is nothing but 1 upon IH cut. I am changing the minus sign by multiplying I and I, right? So it is finally commutation relation between AH and HH. Excellent. Right. Now, see, that's why we had renamed our A, H and HH as we added H in the suffix, right? To differentiate it with Heisenberg picture from Schrodinger picture. Now here, our A, the operator A, it depends explicitly on time, right? That means my dAh by dt has to be del AH by del T plus 1 upon or some structure of this kind, AH, HH. Okay, now this is our Heisenberg equation of motion for the operator AH. Now it is very identical with the previous form, right? And you can see it is also identical to another equation. Can you observe? In classical mechanics, if you look at the Hamiltonian equation for motion, for dynamical variable, it looks like this only.
Yes, sir.
Right?
Poisson brackets.
Yeah, yes. So, of course, it is not the same, but you can see the resemblance. That's what I'm pointing out. That's what mathematical physics and other spatial function helps us to do. Find the resemblance and find the most accurate or try to find exact solution, right? Okay. Going ahead. So if we want to write the equation of motion of expectation value of our operator AH, I hope just my screen froze. Are you able to see AH that I have written? I have made a circle.
Yes, sir.
Okay, perfect. Okay. So if I write it in terms of expectation values, AH, and this equation, as we know from the definition, psi H, AHT, psi H, fine, which will be psi H dAh by dt, psi H, which is going to be 1 upon IH cut AH HH. Okay, how? So using this identity, correct? That's what we have used here for dH by dt, right? That's what we found. So if AH depends explicitly on time, that is, then the expectation value and the rate of change of dynamic variable operator with time, right, is definitely given by, can be given by this equation. H, HH. And their expectation values. So the equation of motion for expectation value in Heisenberg picture and Schrodinger picture are the same if you look at the equations. Only what is happening? In one case, your state vector remains constant. In another case, your dynamic variable remains constant. The operator of dynamic variable remains constant. The last and third picture, right? The interaction picture. When both are varying with time. Okay, so how do we deal with such kind of scenario, right? What kind of system can have this kind of scenario? Many we can think of physically, but in quantum mechanics, how do we go ahead, right? So let's begin with its Hamiltonian. Let's say the Hamiltonian is made up of two parts. One which is independent of time, another which is dependent upon time. Fine. So what we will do is that we are trying to combine the feature of Schrodinger and Heisenberg picture together. Okay. So the Hamiltonian, let's say, is made up of two parts. Time independent and time dependent part. Okay. Now the time development operator, which is our U operator. How did, let's say, our time dependent time development operator, that is U, in absence of, when time dependent component is absent, right? In absence, or not absent, absence of H dash T, that is when we are focusing on this, the operator we are representing as U0, okay, to make a distinction that it is associated with H0. This TT0 exponential minus I upon H cut H0 T minus T0. Okay. And for this particular case, we can say the state vector and our dynamic variable operator, right, which are obtained through unitary transformation in previous cases, right? Schrodinger case, because it's a time independent waves vector. So let me write psi t is equal to U0 inverse TT0 psi t, which was e to the power IH, but here it's a Schrodinger case, so I will use H0 T minus T0 upon H cut into psi t. Okay. Similarly, the dynamic variable, which varies with T, it will be transformed into U0 inverse TT0 A U0 TT0, which will be e to the power I H0 T minus T0 upon H cut, right, into A into e to the power minus I H0 T minus T0 upon H cut psi t. Right. So since this is an interaction picture, I will write I as suffix. So psi and A are part of interaction picture, which are denoting our state vector and dynamic variable operator. Right. So in the absence of time dependent Hamiltonian. So this is psi and A, which is in the absence of time dependent Hamiltonian. Remember that. So here right now we are considering the case where HT is H0 in the interaction picture. Okay. Fine. So what does this show is that when we are considering this H dash T is equal to 0 and we are focusing on this part, then this expression that we get, what does it show? It shows that it is nothing but it's a Heisenberg picture. It coincides with Heisenberg picture. Okay. Fine. Then if let's go ahead, then let's say the state vector psi which is function of t, it is going, let's say, usual time dependent Schrodinger equation. That's what we are used to, right? Usual, it's very not technical to write usual time dependent Schrodinger equation, but that's what we know when we say Schrodinger equation. So what is that? That is simply IH cut del psi t by dt is equal to, in this case, we have two Hamiltonians, h0 plus h dash. So obviously, this is with time to psi t. Okay. So what we are going to do is that we will use this interaction version of psi, and we will differentiate it with respect to t, and we will see what we are getting, so that we can have an idea that what happens to state vector in the interaction picture, which obeys a similar kind of differential equation. Right? Here we saw that it's a similar kind. That means in this case, kind of Heisenberg picture. Okay. So let me begin with this psi it, this equation, e to the power ih0 t minus t0 upon h cut psi t. So we will use that psi it and differentiate it. So it will be d psi it by dt, which will be I upon h cut h0 into e to the power ih0 into t minus t0 upon h cut into psi t plus e to the power I h0 t minus t0 upon h cut into d psi by dt. Okay. Now, just look at this term. So here we have d psi by dt. We have d psi by dt over here, right? So we will use this term substituted here. Fine. So if you rewrite this using the above equation, this will turn out to be I upon h cut h0 psi it plus e to the power I h0 t minus t0 upon h cut into 1 upon, I will write here, but it's in continuous section of the second term. Okay. h0 plus h dash t psi t from this equation. Simplifying it further, let me zoom it. So it will be minus sign out, minus I upon h cut. It will be, how do we transform it into? It turns out, okay. What will happen? Okay, you can see clearly h0 term will get cancelled.
will get cancelled.
Right, perfect, right? So I am cancelling those two terms and we will be left with h dash term only. So e to the power I h0 t minus t0 upon h cut into h dash t into e to the power minus I h0 t minus t0 upon h cut into psi it. Right? So if you look at the equation of this, look at this particular part and look at our interactive wave function equation here, this particular portion, right? And this portion, it gets what? Again, this gets cancelled. Right, right. So again, it is turned out to be minus I upon h cut h dash I into psi it, which is your d psi interaction picture when time varies by dt. Okay, fine. So this is one equation that we have obtained in interaction picture. So we will rewrite this equation and you will find it to be of familiar form. That is IH cut d psi IT by dt is equal to H dash I psi IT. Right? We know what is H dash I. In this equation, H dash IT is nothing but our U0 inverse TT0 H dash U0 TT0. Fine. Now we also have equation of AIT over here. Yes, let me copy it. Right. So yes, this is what you can see. Now, if we differentiate our AIT in interaction picture, right, then you can observe that the rate of change of the operator obeys the equation. Okay, let's not skip it. Let's do it. Okay. So dAI by dt will be equal to del AI by del t. That's what we have observed in the previous cases, but in the interaction picture. So you can see the structure is almost the same. Your AI and HIO are changing with the three pictures beginning from Schrodinger. Fine. Okay, here also, what is our HIO? It is nothing but when H dash t is 0, that is time dependent part is 0, right? So it is represented as U0 inverse TT0 H0 U0 TT0, right? So it is nothing but your H0, but in interaction picture. So you have H dash version and you have H0 version. Okay, so what does it mean? Again, first case here, we showed that our A, where is it? Yes, here, yes, I said that this represented that it is coinciding with Heisenberg picture, right? For our dynamic variable A. But when we look at our state vector, then it is represented like it is represented in Schrodinger picture. So in interaction picture, in the first case, when H dash t was considered 0, when we considered Hamiltonian to be only H0, it shows that the dynamical variable operator shows that it coincides with Heisenberg picture. At the same time, your state vector psi coincides with the Schrodinger picture. Clear? Okay. So let's move ahead from here. It's not
Sorry
yet
to
over.
interrupt you, sir. We have 2 more minutes.
Oh. Okay. So let's. We are about to complete. So I will quickly complete in 3 minutes max. Right. So keeping this in mind, we have to understand that the H dash Hamiltonian operator obeys Heisenberg picture with Hamiltonian H0. So let me quickly mention about H0, H and H dash t. So let's quickly go to UTT0. What is it? U0 T T0, UIT T0 in this case. Interaction picture. Your psi t was, we began with UTT0, psi t0, and here we are with psi it to be UI TT0, psi IT0. What you can do further is that you can again use the unitary operator in the Schrodinger equation and begin with this, that IH cut dui by dt is equal to hi dash ui, and find the expectation value ai, right? You know that psi it AIT psi t, and then you find the rate of change of this dAI by dt, and you will find that the structure is the same as what we have observed. You will come up with this equation. Please try this at home. Del AI del t plus 1 upon IH cut, commutation relation between AI HR. Fine, where HI is finally at 0I plus HI dash. Okay, so I will quickly tell you what we are trying to say is that Schrodinger picture is the one which is widely used, and we are using it in our textbooks and curriculum, right? And all the three pictures are equivalent, right? So you can choose any of the picture that is more convenient to the problem that is presented to you, or the problem that you have taken up. Okay. To have a better understanding about the interaction picture, we will try to complete that time-dependent perturbation theory, right? We will see how the interaction picture is more convenient in time-dependent perturbation theory, right? So in the next class tomorrow, I am planning to discuss linear harmonic oscillator using Schrodinger and Heisenberg picture, along with the matrix mechanism, right? So mostly in Heisenberg picture, we will treat dynamical variable as matrices, not in Schrodinger. So most of you have done the derivation of linear harmonic oscillator using Schrodinger picture, where you had the, you can correlate now, right? So tomorrow we will see that as well as the Heisenberg picture, where we'll use dynamic variable as matrices. Okay, so that's for today's class. Okay, can I give you 2 or 3 problems for the practice?
Yeah, definitely.
Okay, so one problem. Okay, let me give you only one problem. So you are all aware about the Ehrenfest theorem, right? So homework or practice, it's not a compulsory, but if you do it, then it's for the benefit of you only. So try to derive or deduce Ehrenfest theorem using our standard form that we observed today. The d by dt A is equal to 1 upon IH cut AH. So you can derive Ehrenfest theorem for any two dynamical quantity, whether you take it momentum or potential and momentum. It's up to you, force and momentum, whatever the quantity you want to deduce any for any one relation of Ehrenfest using this equation, using this expectation value operator. Okay, I think you can do it. If not, then we can discuss in tomorrow's class. Okay, sir, Gurudat sir, over to you, sir.
Yeah. Thank you.
Thank you,
Mr.
sir.
Sheikh, for this nice lecture. We will see you tomorrow again.
Yes, sir.
Thank you very much. So I'm calling this session off.